The fabric of time, from absolute to relative, classical Newtonian time, it was once an unwavering concept, a universal metronome for all existence. Sir Isaac Newton envisioned time in this very manner. He saw it as a separate, absolute entity flowing onward. It moved uniformly for everyone, everywhere across the cosmos. The same steady tick-tock regardless of an observer's motion or the pull of gravity. This precise view formed the bedrock of physics for many centuries. It was our fundamental understanding of how the universe kept its schedule. This framework felt solid, utterly dependable, and wonderfully predictable to human intuition. Then came Albert Einstein, and our understanding underwent a profound revolution. With his special theory of relativity, time was no longer absolute. Instead, it became relative, its passage dependent on the observer's motion. Imagine this: the faster you move through space, the slower your personal experience of time progresses, relative to someone who is stationary. This was a truly shocking and paradigm-shifting idea. It effectively shattered the long-held Newtonian dream of a single universal time. Einstein revealed that time is more akin to a flowing river, its current changing speed based on the currents of velocity. Our very perception of events happening simultaneously also became relative. Einstein's insights didn't stop there. General relativity added another layer. This theory introduced gravity's remarkable influence on time. Massive objects like planets and stars warp the very fabric of space-time around them. Consequently, time itself slows down in the vicinity of strong gravitational fields. This means a clock placed near a colossal black hole would tick noticeably slower than an identical clock situated on Earth. Time, therefore, is intricately interwoven with the fabric of space, creating a unified four-dimensional continuum known as space-time. It is not merely a passive backdrop for cosmic events, it is an active participant in the universe's unfolding drama. So, time is often called the fourth dimension, an integral part of space-time. Just as we possess the freedom to move in the three familiar spatial dimensions, up and down, left and right, forward and backward, we are all constantly, irresistibly moving through the dimension of time. Einstein's genius was in unifying space and time into this single, cohesive structure. Any event in the universe can be pinpointed by its coordinates in this four-dimensional space-time. This dimensional perspective is absolutely crucial. It theoretically opens the intriguing possibility of navigating time itself, much like we navigate the vastness of space, presenting immense implications for physics and philosophy. Riding the waves of space-time dilation and cosmic tunnels. Time dilation is a fascinating verified consequence of Einstein's relativity. It manifests in two primary forms, affecting the flow of time. Special relativistic time dilation occurs due to relative velocity between different observers. The rule is simple: the faster you decide to travel through space, the slower your personal clock will tick when compared to an observer who remains stationary. This isn't some trick of mechanical clocks, it is time itself that stretches and becomes malleable. It is a fundamental characteristic of how our universe is actually structured. This extraordinary effect only becomes truly significant when speeds approach the cosmic speed limit, the speed of light. The practical implications of time dilation are not just theoretical, they are part of our daily lives. Global Positioning System, GPS satellites, orbiting high above Earth, must constantly correct for time dilation effects. Their onboard atomic clocks experience both special relativistic effects due to their high orbital speeds and general relativistic effects because they are in a weaker gravitational field than we are on the surface. Without these precise relativistic corrections, your GPS navigation would rapidly become inaccurate, off by several kilometers each day. For hypothetical future travel near light speed, astronauts would age much slower than people remaining on Earth. A journey to a distant star and back could see decades pass on our planet while mere years elapse for the intrepid space travelers. Now, let's explore wormholes, often described as theoretical time portals. These are fascinating solutions that emerge from Einstein's complex field equations in general relativity. They are also known by the more formal name, Einstein-Rosen bridges. These are essentially hypothetical tunnels, or shortcuts, through the fabric of space-time. Such a tunnel could, in theory, connect two vastly distant points in space, allowing for much faster-than-light effective travel. Or, even more tantalizingly, a wormhole might connect two different points in time, offering a pathway to the past or future. Imagine folding a sheet of paper, representing space-time, and punching a hole through the aligned sections. However, there is a significant catch: stabilizing these cosmic shortcuts. This presents a major theoretical and practical challenge. Most currently understood wormhole solutions are inherently unstable. They would likely collapse in an instant if any matter or even a single photon attempted to pass through them. To keep a wormhole open and traversable, physicists believe we would need something truly extraordinary exotic matter. This is not the ordinary matter we see around us. Exotic matter would need to possess bizarre properties, such as negative mass energy density. Such peculiar material has never been definitively observed in nature, and creating it remains a monumental, perhaps insurmountable task for future generations of scientists. Exotic architectures for time travel, theoretical constructs. Beyond wormholes, other exotic architectures for time travel have been proposed, like cosmic strings. These are hypothetical, one-dimensional topological defects in space-time. Physicists theorize that they might have formed during the tumultuous conditions of the very early universe, fractions of a second after the Big Bang. These strings, if they exist, would be incredibly dense structures. They would be thinner than an atom's nucleus, yet possess an immense amount of mass concentrated per unit length. Such extreme density would allow them to warp space-time around them quite significantly. Some theories suggest that if two such super-dense cosmic strings were to pass each other at speeds approaching that of light, they could create conditions allowing for closed time-like curves, regions of space-time where you could, theoretically, travel into your own past. Another intriguing, though highly theoretical concept, is the Tipler cylinder. This idea was proposed by the physicist Frank J. Tipler in the 1970s. Imagine an incredibly long, perhaps infinitely long cylinder composed of super-dense material. This cylinder would then need to be spun on its longitudinal axis at a rotational speed approaching the speed of light. The combination of immense mass and rapid rotation would, according to general relativity, drag space-time around it. This phenomenon is known as frame dragging. If this effect were extreme enough, it could theoretically create pathways or trajectories that loop back in time. A brave spaceship, by following a precise spiral path around this spinning cylinder, could potentially travel into the past. However, the requirement of infinite length, or at least unimaginably vast dimensions, presents a significant practical hurdle to its construction. The quest for a theory of quantum gravity plays a crucial role in these discussions. Currently, our understanding of the universe is governed by two incredibly successful, but ultimately incompatible theories. General relativity beautifully describes gravity and the large-scale structures of the cosmos, like galaxies and black holes. Quantum mechanics, on the other hand, describes the other fundamental forces and the bizarre world of subatomic particles. A theory of quantum gravity would unify these two frameworks. It would provide us with a much deeper and more complete understanding of space-time's true nature at the most fundamental level imaginable, the Planck scale. At this tiny scale, space-time itself might be quantized, existing in discrete units. Unlocking the secrets of quantum gravity might reveal that space-time is not the smooth, continuous fabric we often imagine. Instead, it could be a quantum foam, a turbulent sea of tiny, fleeting wormholes and other exotic geometries constantly appearing and disappearing at an unimaginably small scale. If humanity could ever understand and then manipulate these quantum effects, entirely new avenues for time travel might emerge. These methods could be fundamentally different from the macroscopic structures like Tipler cylinders or large, stable wormholes. It might involve directly manipulating the very fabric of reality at its most basic level, opening new, currently unforeseen vistas for temporal exploration and discovery in the distant future. Journey to 2256, Hopes, Hurdles, and Temporal Puzzles. Peering into the future, say to the year 2256, what are the possibilities for achieving time travel? This remains a highly speculative outlook, of course. Humanity might make truly significant strides in fundamental physics by then. Mastering a complete theory of quantum gravity is almost certainly a key prerequisite. This monumental endeavor could take many decades or even centuries of dedicated research by brilliant minds. If such a theory is achieved, it would undoubtedly revolutionize our entire understanding of the universe and its laws. Theoretical breakthroughs would then need to be followed by rigorous experimental verification, and then, the colossal engineering challenges of manipulating spacetime would begin. Harnessing exotic matter and leveraging advanced artificial intelligence will be critical. As mentioned, exotic matter with properties like negative mass energy density remains a crucial ingredient for stabilizing wormholes or powering other spacetime bending technologies. Discovering such matter, or learning how to engineer it, represents a monumental scientific and technological task. Advanced artificial intelligence could prove to be an invaluable partner in this quest. AI systems could perform the incredibly complex calculations required for quantum gravity theories. They could run sophisticated simulations of space-time manipulations, and even help us understand or perhaps control the extreme gravitational effects associated with miniature black holes. These advanced tools will be vital for progress. However, we must acknowledge the immense energy requirements involved. This is a persistent and formidable challenge for most proposed time travel theories. The amount of energy needed to warp space-time significantly enough to create, for instance, a traversable wormhole or a functioning Tipler cylinder is simply astronomical. We are talking about energies comparable to the total output of a star, or perhaps even the energy equivalent of entire galaxies. Manipulating matter and energy on such colossal scales is far, far beyond our current technological capabilities, and likely our capabilities for centuries to come. This energy hurdle alone might make macroscopic time travel impractical for a very long time, if not rendering it permanently out of reach. Ultimately, time travel remains a profound and captivating mystery, shrouded in theoretical complexities and potential paradoxes. Causality paradoxes, such as the famous grandfather paradox, what if you went back in time and prevented your own grandfather from meeting your grandmother? Pose serious logical problems. How would the universe resolve such glaring inconsistencies in the timeline? Some theories propose a principle of self-consistency, suggesting that history cannot actually be changed in a paradoxical way. Others speculate about the creation of parallel universes with each temporal intervention. The fundamental laws of physics might even have built-in protections against such temporal tinkering, a concept Stephen Hawking called the chronology protection conjecture. For now, the door to the past remains firmly and perhaps wisely closed to us.